What if everything we've ever known about the universe, its swirling galaxies, its racing planets, even the very fabric of space itself, was just an illusion? Picture a cosmos frozen in time, where nothing moves, nothing spins, nothing expands, no drifting stars, no colliding galaxies, just an endless, silent stillness. It sounds impossible, doesn't it? After all, we've been taught since childhood that the universe is a dynamic, ever-changing place. But what if that's not the whole story? What if, hidden beneath the surface of our observations, lies a truth so startling it could upend centuries of scientific understanding? This is the mystery of the motionless universe, a theory that dares to challenge the very foundations of astronomy. For generations, we've looked to the heavens and seen motion everywhere. Planets orbit their stars, galaxies hurtle through space, and even the universe itself stretches outward in a relentless expansion. But what if all of this movement is just a trick of perspective? What if the universe isn't expanding at all, but instead something far stranger is happening? The idea of a motionless cosmos isn't just science fiction, it's a real, if controversial, scientific proposition. Some researchers argue that the evidence we've interpreted as motion could actually be pointing to an entirely different reality. Imagine standing on a train platform, watching another train pull away. For a moment, you might feel like you're the one moving backward. Could the universe be playing a similar trick on us? This isn't just about rewriting textbooks, it's about reimagining reality itself. If the universe isn't moving the way we think it is, then everything from the Big Bang to dark energy might need a second look. The implications are staggering. Could Einstein's theories, the bedrock of modern physics, need revisiting? Might there be forces or phenomena at work that we haven't even begun to understand? In this video, we'll dive deep into the origins of this radical idea, the evidence that supports it, and the fierce debates it sparked among scientists. We'll meet the thinkers who have dared to question the status quo and explore why their ideas could change everything. So buckle up, because by the time we're done, you might never look at the night sky the same way again. To understand why the idea of a motionless universe is so radical, we first need to revisit how humanity came to see the cosmos as a place of constant movement. It all began with the simple act of looking up. Ancient civilizations tracked the wandering paths of planets against the backdrop of fixed stars, noticing patterns that repeated with clockwork precision. When Isaac Newton formulated his laws of motion and gravity in the late 17th century, he gave mathematical structure to these observations, showing how celestial bodies move in response to invisible forces. For the first time, the heavens weren't just mysterious lights in the sky. They obeyed predictable rules, but Newton's universe had its limits. His laws worked beautifully for planets orbiting the sun, but they couldn't explain everything. Centuries later, Albert Einstein's theory of relativity rewrote the rules again, revealing that space and time weren't just a static stage for cosmic motion. They were part of the performance itself. According to Einstein, gravity wasn't a force pulling objects together, but the result of massive objects warping the very fabric of spacetime. This elegant framework explained phenomena Newton couldn't, like the subtle wobble in Mercury's orbit or the way light bends around stars. It also painted a picture of a dynamic, ever-changing universe, one where galaxies raced apart in a grand cosmic expansion. Yet not everyone accepted this vision without question. Even as Einstein's ideas gained traction, a handful of scientists dared to propose alternatives. In the early 20th century, astronomer Fritz Zwicky noticed something peculiar about galaxy clusters. Their motions didn't always match predictions. He suggested that unseen, dark matter might be influencing their behavior, but others wondered if the problem lay deeper. Could the apparent motion of galaxies be an illusion? Around the same time, physicist Paul Dirac speculated that the constants of nature, like the speed of light or the strength of gravity, might change over time, a hint that the universe's behavior wasn't as fixed as it seemed. These dissenting voices were often dismissed, their ideas labeled as fringe or unorthodox. After all, the evidence for cosmic motion seemed overwhelming. Edwin Hubble's observations in the 1920s showed galaxies receding from us, their light stretched into redder wavelengths, a phenomenon we now call redshift. This became the cornerstone of the expanding universe theory, bolstered later by the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang. But what if there's another way to interpret these clues? What if redshift isn't caused by galaxies speeding away but by something else entirely, like light losing energy as it travels across unimaginable distances? The foundations of modern cosmology rest on the assumption that what we see reflects reality. But history has taught us that scientific truth often hides in the gaps between observations. Just as Einstein revealed the limitations of Newton's worldview, could we be on the verge of another revolution? The motionless universe theory doesn't just challenge our understanding of movement, it invites us to reconsider how we interpret every signal from the cosmos. And if even a fraction of its claims hold weight, the implications could redefine not just where we are in space, but how we perceive the universe itself. If the universe isn't expanding, then one of the most fundamental ideas in modern cosmology, the Big Bang, suddenly stands on shaky ground. For decades, the Big Bang theory has been the cornerstone of our understanding, painting a dramatic picture of an infinitely dense point exploding outward, creating space, time, and everything we know. But what if the evidence supporting it isn't as ironclad as we've been led to believe? Take redshift, for example. When astronomers observe distant galaxies, the light reaching us appears stretched, shifting toward the red end of the spectrum. The standard explanation is simple. Space itself is expanding, stretching the light waves as they travel, like ink dots on an inflating balloon moving apart. This interpretation led directly to the idea of an expanding universe. But what if there's another explanation? Some scientists argue that redshift could instead be caused by light gradually losing energy over vast cosmic distances, a phenomenon known as tired light. In this view, galaxies aren't racing away from us. Their light is simply changing as it journeys across the cosmos. Then there's the cosmic microwave background radiation, often called the echo of the Big Bang. This faint glow, discovered in the 1960s, is thought to be the cooled remnants of the universe's fiery birth. But critics point out that a static universe could also produce similar radiation through other means. For instance, if light from countless stars and galaxies scattered and interacted over eternity, it might eventually smear into a uniform glow, no explosive beginning required. The most vocal challengers to the Big Bang have proposed radical alternatives. Take physicist Holton Arp, who spent decades cataloging strange cosmic anomalies, galaxies with mismatched redshifts or objects that seemed physically connected despite supposedly being billions of light-years apart. His observations suggested that redshift might not always indicate distance or motion, undermining a key assumption of expansion. Meanwhile, Nobel laureate Hans Alfvén proposed a plasma universe model where electromagnetic forces, not gravity, shape cosmic structures, eliminating the need for an initial singularity. Of course, these ideas remain controversial. Mainstream cosmology still overwhelmingly favors the Big Bang, backed by sophisticated computer models and precise measurements. But science advances when someone dares to ask, what if we're wrong? The motionless universe theory forces us to re-examine the very foundations of our cosmic story. If redshift and the microwave background can be explained without expansion, then the Big Bang might not be the only game in town, and that opens the door to an even bigger question. If the universe isn't expanding, what's really happening out there? The notion of a static universe, one that has always existed, unchanging and eternal, flies in the face of modern cosmology. Yet for a growing number of scientists, this idea isn't just a thought experiment. It's a framework that could resolve some of astronomy's most stubborn mysteries. Take the distribution of galaxies, for instance. Surveys of the cosmos reveal vast, bubble-like structures with galaxies clustered along filaments, separated by enormous voids. The Standard Model explains this as the result of cosmic expansion stretching primordial density fluctuations over billions of years. But what if these patterns aren't relics of an ancient explosion? Some researchers point out that similar structures could emerge naturally in an infinite, ageless universe where gravity has had eternity to sculpt matter into these intricate webs. Then there's the puzzle of dark energy, the mysterious force thought to be accelerating the universe's expansion. Measurements of distant supernova in the late 1990s suggested the cosmos was flying apart faster than expected, earning their discoverers a Nobel Prize. But dark energy has always been a slippery concept, an invisible, all-pervasive influence with no known physical origin. In a static universe, this conundrum vanishes. Without expansion, there's no need to invent dark energy to explain it. Instead, redshift could arise from other mechanisms, like light interacting with sparse interstellar particles over cosmic distances, an idea first proposed by astronomer Fritz Zwicky nearly a century ago. Critics often dismiss static models as outdated, recalling Einstein's abandoned cosmological constant, a tweak to his equations meant to preserve a steady-state universe before Hubble's discovery of expansion. But today's proponents aren't reviving old mistakes. They're grappling with new anomalies. For example, certain galaxies appear far too mature for their supposed age in an expanding cosmos, their stars seemingly older than the universe itself. Others exhibit quirks in their rotation speeds that don't neatly fit dark matter predictions. Could these inconsistencies hint that we've misread the cosmic timeline entirely? Perhaps the boldest claim of static universe theorists is that the Big Bang's most celebrated evidence, the cosmic microwave background, might have another explanation. If starlight were endlessly absorbed and re-emitted by cosmic dust over infinite time, it could produce a uniform glow indistinguishable from a primordial fireball's echo. Even the precise temperature variations in the background radiation, often called the fingerprint of the Big Bang, might instead reflect the clumpy distribution of matter in an eternal cosmos. Of course, this isn't to say the static universe model has all the answers. It must contend with its own challenges, like explaining why quasars' extremely bright galactic cores show such extreme redshifts if not from motion. Yet the very existence of these debates underscores a profound truth. Science progresses when we question even our most cherished assumptions. Whether the universe is expanding or standing still, the real discovery lies in realizing how much we have yet to understand. Redshift, the stretching of light toward the red end of the spectrum, has long been astronomy's smoking gun for an expanding universe. When Edwin Hubble first noticed this shift in the light from distant galaxies, it seemed obvious. Space itself was stretching, carrying galaxies away like leaves on a rushing river. But science thrives on questioning the obvious. What if redshift isn't a cosmic speedometer after all? What if it's something far stranger? One compelling alternative is gravitational redshift. Einstein predicted this phenomenon himself: light struggling to escape a massive object, like a star or black hole, loses energy, stretching its wavelength toward the red. But could this happen on a universal scale? Imagine if the fabric of space itself had subtle variations in gravity's grip, like invisible hills and valleys. Light traveling through these regions might redshift without any actual motion, like a hiker slowing as they climb a steep trail. Some theorists suggest that if the universe is filled with unevenly distributed mass, clumps of dark matter or hidden structures, their gravitational influence could mimic the effects of expansion. Then there's the controversial tired light hypothesis, proposed nearly a century ago by Fritz Zwicky. It suggests that light might simply lose energy as it travels across cosmic distances, not because space is expanding, but because photons interact with the sparse particles floating in the void. Think of it like a marathon runner gradually losing stamina over miles. The light arrives redder not because the finish line is moving away, but because the journey itself changed it. Critics argue this would blur distant galaxies more than we observe, but proponents point to quantum fluctuations or unknown particle interactions that might preserve clarity while still sapping energy. Even more radical is the idea that the speed of light isn't constant. What if photons slowed down over time, stretching their wavelengths in the process? This would mean redshift isn't about motion at all, it's a sign of light itself aging across the eons. While mainstream physics treats light's speed as inviolate, a handful of researchers speculate that in the early universe, conditions might have been different. If true, it would turn redshift from a measure of cosmic flight into a cosmic clock, ticking silently in the light of distant stars. The beauty of these alternatives isn't just that they challenge the expanding universe, they force us to ask deeper questions about how we interpret the cosmos. Every observation relies on assumptions, that light behaves predictably, that gravity follows known rules, that the universe is uniform. But what if those assumptions are incomplete? When we look at redshift, we're not just seeing distant galaxies, we're seeing our own theories reflected back at us. And sometimes, the most revolutionary discoveries begin when someone dares to wonder if the reflection is distorted. Galaxies spin like cosmic whirlpools, their stars tracing vast, graceful arcs around a central hub. But there's a problem. The way they rotate defies expectations. According to Newton's laws, stars on the outer edges should move slower, like planets farther from the sun. Yet when astronomers measured these rotations, they found something shocking. Outer stars whip around just as fast as inner ones, as if gripped by some unseen hand. This anomaly was so glaring that scientists invented an entire new form of matter-dark matter to explain it. But what if the answer isn't hidden in some mysterious substance? What if we've misunderstood the nature of motion itself? Enter the idea of a static universe. In this radical framework, the strange behavior of galactic rotation curves might not require dark matter at all. Instead, the discrepancy could arise from how we interpret gravity's role in a motionless cosmos. One compelling theory suggests that in a universe without expansion, the gravitational forces between stars and galaxies might operate differently over vast distances. Picture a spiderweb stretched taut, tug one thread, and the tension radiates outward in ways that aren't immediately obvious. Similarly, in a static cosmos, the collective pull of countless stars could create subtle, large-scale effects that mimic the presence of invisible matter. Another possibility lies in the way light behaves over cosmic distances. If redshift isn't a sign of galaxies speeding away, but instead stems from some intrinsic property of light or space, then our calculations about galactic masses and motions could be fundamentally flawed. We might be misreading the speed of stars because we're misinterpreting the very signals they send us. It's like trying to judge the speed of a car by the sound of its horn. if the horn's pitch changes for reasons unrelated to motion, our entire estimation falls apart. Perhaps most intriguing is the work of physicists who have tweaked the laws of gravity itself. Modified Newtonian dynamics, or MND, proposes that gravity doesn't weaken as sharply over large distances as Newton and Einstein predicted. In a static universe where the fabric of space isn't stretching, such adjustments could neatly explain why outer stars don't slow down, no dark matter required. Critics argue MND struggles to account for all observations, but its proponents point to surprising successes, like accurately predicting the rotation of certain galaxies where dark matter models falter. The implications are profound. If galactic rotations can be explained without invoking dark matter, it wouldn't just simplify our cosmic models, it would force us to rethink one of astronomy's biggest mysteries. After decades of searching, dark matter particles have never been directly detected, despite countless experiments. Could their elusiveness be a clue that we've been chasing a phantom? The static universe hypothesis offers a daring alternative. Maybe the universe isn't hiding anything from us. Maybe we've just been reading its signals wrong all along. This isn't about discarding the scientific method, it's about pushing it further. Every major breakthrough in astronomy has come from questioning assumptions, from Copernicus moving the sun to the center of the solar system to Hubble revealing the cosmos's expansion. Now, as we stare at those stubborn rotation curves, we're faced with another pivotal question. Do we double down on the hunt for dark matter, or do we consider that the answer might lie not in what's missing, but in how we've framed the problem? The static universe model doesn't just challenge a theory, it challenges us to see the heavens with fresh eyes. The Nobel Prize-winning discovery that the universe's expansion is accelerating shook cosmology to its core. Astronomers observed distant supernova glowing dimmer than expected, as if space itself were stretching faster over time. The explanation, a mysterious force dubbed dark energy, pushing galaxies apart with relentless strength. But what if this groundbreaking revelation rests on a colossal misunderstanding? What if the universe isn't accelerating at all? Critics of dark energy point to a subtle but critical assumption buried in the data. The idea that supernova, the cosmic mile markers used to measure expansion, behave the same way everywhere and everyone. Imagine using candles to judge distances in a foggy forest. If some candles burned brighter in the past, or if interstellar dust dimmed their light unevenly, your map would be wildly off. Similarly, if ancient supernova differed from modern ones, perhaps due to changes in stellar composition over billions of years, their dimming might signal evolution, not acceleration. Even tiny biases in these measurements could skew our entire cosmic narrative. Then there's the elephant in the room, dark energy itself. Despite dominating the universe's energy budget, it remains a phantom. No one knows what it is, where it comes from, or why it kicked in so late in cosmic history. Some theorists argue that the acceleration signal might instead stem from our own motion through space. Picture standing on a train platform as an express roars past. For a split second, the world around you seems to lurch. If our galaxy is drifting through a region of uneven gravity, that motion could warp our perception of the wider universe, creating the illusion of acceleration. Others propose that Einstein's equations, the bedrock of cosmology, might need tweaking on cosmic scales. Just as Newton's laws faltered near black holes, relativity could have blind spots when applied to the universe as a whole. Modified gravity theories suggest that what we call dark energy might actually be space's innate curvature, reacting to vast cosmic structures like a trampoline sagging under the weight of invisible masses. The most radical idea, time itself might be the culprit. If the flow of time varied across the cosmos, slowing in denser regions, speeding up in voids, our measurements could be hopelessly tangled. Light from ancient supernova might appear redshifted not because space expanded, but because time ran differently when those stars exploded. It's a dizzying thought. The universe's acceleration could be a mirage, a side effect of deeper, stranger physics we've yet to uncover. This isn't just academic nitpicking. If dark energy doesn't exist, our predictions for the universe's fate, a cold, lonely rip apart trillions of years from now, could be dead wrong. Instead of a runaway expansion, the cosmos might settle into a quiet equilibrium, or even cycle through phases we can't yet imagine. The Nobel Prize wasn't a mistake, but it might have been a stepping stone. Every revolutionary idea in science begins by questioning the last one, and the mystery of cosmic acceleration is far from solved. Einstein's original vision of the cosmos was one of perfect stillness, a universe neither expanding nor collapsing, but eternally balanced. To make his equations reflect this, he introduced a fudge factor, a tiny mathematical tweak he called the cosmological constant. It represented a repulsive force, counteracting gravity's pull to keep the universe frozen in equilibrium. But when Edwin Hubble's observations revealed galaxies fleeing from one another, Einstein famously abandoned the idea, calling it his greatest blunder. He removed the constant from his equations, and the expanding universe became the cornerstone of modern cosmology. Yet history has a way of circling back. Decades later, astronomers discovered that the universe's expansion wasn't just continuing, it was speeding up. Suddenly, scientists needed a repulsive force to explain this acceleration. Guess what they resurrected? Einstein's cosmological constant, now rebranded as dark energy. The irony is almost poetic. The very idea Einstein discarded might be the key to understanding the cosmos after all. But here's the twist: what if he was right for the wrong reasons? What if the universe isn't expanding at all, and his original static model was closer to the truth? Modern theorists have taken Einstein's abandoned constant and given it new life, not as a counterbalance to expansion, but as a clue to a deeper mystery. Some propose that the cosmological constant might not represent dark energy's push, but something far stranger, a signature of a universe where space itself has intrinsic energy, a sort of background hum woven into the fabric of reality. Picture a vast, motionless ocean, its surface perfectly calm, yet teeming with invisible currents beneath. In this view, redshift and other cosmic phenomena might not signal motion, but interactions with this hidden energy field. Others suggest that Einstein's blunder wasn't the constant itself, but his assumption that the universe needed to be perfectly static. What if it's neither expanding nor motionless, but something in between? Certain modified gravity theories propose that the cosmos undergoes slow, subtle shifts, not explosive growth, but gentle ripples in spacetime that mimic acceleration. It's like mistaking the slow rise of dough for an oven's heat. The change is real, but the cause isn't what we assumed. The most radical reinterpretation comes from quantum physics. If empty space crackles with fleeting particles popping in and out of existence, a phenomenon called vacuum energy, this could manifest as a cosmological constant. In a static universe, this quantum frenzy might not drive expansion, but create the illusion of it by altering how light travels. Imagine a hall of mirrors where reflections distort not because the room stretches, but because the glass itself has hidden properties. Einstein's greatest mistake might yet become his greatest legacy. Whether the cosmological constant explains dark energy, reveals a static cosmos, or points to uncharted physics, one thing is clear: science thrives when even discarded ideas get a second look. After all, progress isn't just about being right. It's about daring to be wrong and learning why. quantum mechanics paints a picture of a universe buzzing with activity at the smallest scales, particles jittering in uncertain positions, electrons leaping between energy levels, fields fluctuating in a ceaseless dance. It's a realm where motion seems fundamental, where stillness would defy the very rules governing reality. But what if this quantum frenzy isn't what it appears? What if the microscopic chaos we observe is just the surface ripple of a deeper, motionless foundation? One provocative idea comes from physicist David Bohm, who proposed that quantum particles only seem unpredictable because we're seeing shadows of a hidden order. In his pilot wave theory, particles aren't dancing randomly, they're guided by invisible waves in a static, underlying field. Picture a leaf floating on a perfectly still pond. From above, its path might seem erratic, buffeted by unseen currents, but beneath the surface there's no true motion, just the leaf responding to the pond's silent structure. Bohm's universe operates similarly. What we call quantum motion might be the illusion of particles navigating an unchanging, invisible landscape. Then there's the notion of quantum foam, the seething fabric of space-time at unimaginably tiny scales. Mainstream physics treats this as evidence of constant energy fluctuations, a universe that never sits still. But some theorists suggest this foam could be frozen in time, its apparent turbulence a fixed, eternal pattern. Imagine a stormy ocean captured in a photograph. The waves look dynamic, but the image itself is static. In this view, quantum behavior isn't about movement, it's about how we perceive a complex, motionless geometry. Even entanglement, quantum mechanics' spookiest phenomenon, might fit a static cosmos. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, but in a motionless universe, entanglement could reflect a deeper connectedness woven into space itself, like two points on a frozen tapestry, forever linked by the threads between them. There's no signal traveling faster than light, no hidden motion, just an unchanging network of relationships we're only beginning to map. The real challenge lies in reconciling quantum probabilities, the idea that particles exist in multiple states until observed. How can a static universe account for this apparent randomness? One radical answer: time isn't a flowing river but a fixed landscape where every possible outcome already exists. What we perceive as probability is just our limited view of an eternally branching structure. Think of a stained glass window. From afar, it seems to shimmer and change with the light, but up close, every color and shape is immovably set in place. Critics argue that denying quantum motion ignores decades of experimental evidence, from the double-slit experiment to quantum computing. But proponents counter that these phenomena might not require true movement, just a richer understanding of stillness. After all, a shadow puppet show creates the illusion of motion without the puppets ever leaving the wall. Could quantum mechanics be the universe's own shadow play, hinting at a reality far stranger than we've dared to imagine? This isn't about discarding quantum theory, it's about peeling back its layers to ask what's beneath. Whether the cosmos is eternally still or perpetually in flux, one truth remains: the deeper we look, the more the universe defies our intuition. And that's where the most thrilling discoveries begin. Time might feel like the most constant force in our lives, the steady tick of a clock, the unstoppable march from past to future. But in a motionless universe, this familiar flow could be nothing more than a grand illusion. Think about how we measure time: the swing of a pendulum, the vibration of atoms in an atomic clock, even Earth's rotation, all rely on motion. If the cosmos is truly frozen, then time as we know it loses its anchor. So what does that leave us with? Some physicists argue that time itself could be an emergent property, a side effect of change rather than a fundamental feature of reality. Imagine a movie paused on a single frame. Without movement between frames, there's no sequence, no before or after. In this view, time isn't a river flowing, it's the ripple we mistake for the current. The ancient Greek philosopher Parmenides hinted at this millennia ago when he claimed that change was impossible, that all apparent motion was deception. Modern theories like Julian Barber's timeless physics take this further, suggesting that what we call time is just a vast collection of static nows, arranged in a way that creates the illusion of passage. But if time doesn't flow, how do we explain memory, aging, or cause and effect? One radical possibility is that these phenomena are embedded in the structure of a frozen universe, like grooves in a vinyl record. The needle moves, creating the experience of music, but the record itself doesn't change. Similarly, our consciousness might travel through a static cosmos, giving us the sensation of duration while the universe remains eternally still. This idea, called the block universe theory, treats past, present, and future as equally real fixed coordinates in an unchanging four-dimensional landscape. Then there's the quantum perspective. If particles at the smallest scales behave probabilistically, their apparent randomness might not require time at all. Instead, every possible outcome could exist simultaneously in a vast, frozen probability field. Picture a kaleidoscope. Each twist reveals a new pattern, but the glass fragments themselves never move. In this scenario, what we perceive as time is just our limited view of an infinitely complex, unmoving tapestry. Critics counter that denying time's reality flies in the face of thermodynamics, the irreversible increase of entropy, the universe's tendency toward disorder. But even entropy might fit a static cosmos if disorder isn't a process but a pre-existing feature, like cracks in a frozen lake. The real challenge isn't just redefining time, it's reimagining how consciousness, causality, and even meaning fit into a universe where when is as illusory as motion. Perhaps the most mind-bending implication is that a motionless cosmos doesn't just eliminate time, it erases the distinction between events. Without change, there's no difference between the birth of a star and its death, between the Big Bang and heat death. Everything simply is in an eternal, unchanging tableau. It's a vision that defies intuition, but that's precisely why it's worth exploring. After all, the universe owes us no obligation to make sense. The deeper we dig into these ideas, the clearer it becomes. If the cosmos is frozen, then time isn't just broken, it's a story we've been telling ourselves all along. The idea of a motionless universe isn't the only challenge to mainstream cosmology. Over the last century, several bold theories have dared to reimagine the cosmos without relying on expansion, each offering its own explanation for the universe's structure and behavior. Take the steady-state theory, popularized in the mid-20th century by astronomers Fred Hoyle, Hermann Bondi, and Thomas Gold. Unlike the Big Bang's explosive beginning, their model proposed an eternal, unchanging universe where matter continuously forms to fill the gaps left by receding galaxies. No starting point, no dramatic collapse, just an infinite cosmic equilibrium. At first glance, it sounds elegant, but when the cosmic microwave background was discovered, radiation that seemed to scream Big Bang, the steady-state model fell out of favor. Yet some researchers still argue that a refined version could explain the data without invoking a singular origin. If matter creation occurs in subtle ways, or if the background radiation has other sources, the steady-state cosmos might not be dead, just waiting for its next act. Then there's plasma cosmology, championed by Nobel laureate Hans Alfvén. This theory flips the script entirely, suggesting that electromagnetism, not gravity, shapes the universe's largest structures. Picture a cosmos threaded with vast electric currents, sculpting galaxies and powering quasars like cosmic neon signs. In this view, redshift isn't about expansion. It's the result of light interacting with magnetized plasma across interstellar space. Plasma cosmology's strength lies in its laboratory-backed physics. We know how plasma behaves in experiments, unlike the elusive dark matter and dark energy. But critics point to gaps in its ability to explain the universe's large-scale uniformity or the precise patterns in the cosmic microwave background. Still, its emphasis on observable forces offers a refreshing contrast to the invisible scaffolding of mainstream models. More radical still is the electric universe hypothesis, which takes plasma cosmology further, proposing that even stars and planets are powered by galactic-scale electrical discharges. Imagine the sun not as a nuclear furnace but as a glowing node in a celestial circuit. While this idea captures the imagination and has gained a fervent following, it struggles with quantitative predictions. Without rigorous mathematical support or consensus from observational data, it remains on the fringe. Yet its existence underscores a vital truth. When mainstream science leaves puzzles unsolved, alternative ideas rush in to fill the void. So how do these unorthodox models stack up against the expanding universe? Each has its merits. Steady-state theories sidestep the Big Bang's singularity, a point where physics itself breaks down. Plasma cosmology grounds its explanations in known electromagnetic phenomena rather than hypothetical dark matter. But they also face hurdles. Without expansion, explaining the cosmic microwave background's precise temperature requires creative fixes. The distribution of galaxies, the abundance of light elements, even the time dilation seen in distant supernovae, all were neatly accounted for by the Big Bang. Yet the fact that alternatives persist, evolving to address new data, keeps cosmology honest. Science advances when ideas collide, when no theory gets too comfortable. The real lesson here isn't about which model is right, it's about the power of questioning. Every major shift in astronomy, from geocentrism to relativity, began with someone daring to say, "What if we've been wrong all along?" Whether the universe moves or stands still, one thing is certain. The cosmos has more surprises in store, and the next revolution might be hiding in plain sight, waiting for the right mind to uncover it. Our telescopes are like time machines, peering across the cosmos to capture light that's traveled millions, sometimes billions, of years to reach us. But what if these incredible instruments aren't just revealing the universe's secrets? What if they're also tricking us? The very tools we rely on to measure cosmic motion might be painting an illusion, distorting reality in ways we're only beginning to understand. Take parallax, for example. When astronomers track a star's apparent shift against distant background objects as Earth orbits the Sun, they use this tiny angle to calculate stellar distances. But what if that background isn't as fixed as we assume? If reference points themselves are moving in subtle, undetected ways, our entire cosmic distance ladder could be wobbling beneath us. Then there's the challenge of instrumental bias. Modern telescopes don't just collect light, they process it through layers of software designed to filter noise and enhance signals. These algorithms are trained on expectations, how a galaxy should look, how redshift should behave. But when we program our tools to find what we're already looking for, we risk creating self-fulfilling prophecies. It's like tuning a radio to only pick up stations playing your favorite song. You might miss the symphony playing just outside your frequency. Some astronomers argue that certain features of cosmic expansion, like the uniformity of redshift across the sky, could be artifacts of these very filters, not the universe itself. Even the speed of light, our most trusted cosmic constant, might not be immune to observational quirks. If interstellar space isn't perfectly empty, if it's laced with sparse gas, dust, or fields we haven't mapped, light could slow imperceptibly during its epic journey, subtly altering the redshifts we interpret as motion. Imagine shouting across a windy canyon. Your voice might reach the other side fainter and distorted, not because you moved, but because the air itself stole its energy. Similarly, the universe could be filled with invisible winds bending light in ways that mimic expansion. Perhaps the most unsettling possibility is that our entire observational framework rests on a flawed assumption that the laws of physics are the same everywhere. But what if gravity, light, or even time operate differently in distant reaches of space? Early universe quasars, for instance, exhibit baffling properties that defy standard models. If the rules change across cosmic distances or epochs, then the motions we're measuring might not be motion at all, just the universe refusing to play by the same playbook everywhere. This isn't about dismissing our instruments, it's about recognizing their limits. Every revolutionary leap in astronomy has come with new ways of seeing, from Galileo's crude telescope to Hubble's deep field imaging. But each breakthrough also revealed how much we'd missed before. The motionless universe hypothesis isn't a rejection of science. It's a reminder that every observation is a conversation between the cosmos and our imperfect tools. And sometimes the most profound truths emerge when we stop assuming we know what the universe is saying and start listening more carefully. Mathematics has always been the language of the cosmos, translating the universe's mysteries into elegant equations. But what happens when those equations are rewritten to describe a world without motion? The challenge isn't just about removing variables, it's about rebuilding physics from the ground up while still explaining everything we see. Take Einstein's field equations, the backbone of general relativity. They famously describe how matter and energy warp space-time, creating what we perceive as gravity. In an expanding universe, these equations include a dynamic term, the Hubble constant, to account for the stretching of space, but in a static cosmos, that term vanishes, leaving theorists to ask, how do we explain the same observations without it? One approach tweaks the equations themselves, introducing subtle modifications that preserve gravity's effects while freezing the universe in place. Imagine a spiderweb so perfectly tensioned that every strand stays taut without sagging or shifting. Some models achieve this by adding extra dimensions, mathematical scaffolding that stabilizes spacetime without requiring expansion. Others propose that what we call motion is actually a geometric illusion, like watching a spiral drawn on a spinning disk and mistaking the pattern for movement. The math behind these ideas isn't just abstract tinkering. It's a daring attempt to reconcile a motionless universe with the redshifts and cosmic structures we observe. Then there's the puzzle of light's behavior. In standard cosmology, redshift is a kinematic effect, the result of galaxies racing away. But static models replace this with alternative mechanisms, like light losing energy as it traverses vast distances. The mathematics here draws from older, often overlooked theories. For example, Fritz Zwicky's tired light hypothesis can be expressed as a simple logarithmic decay function, where a photon's energy diminishes proportionally to the space it crosses. Critics argue this would blur distant galaxies more than we observe, but proponents counter with refinements, tiny interactions with quantum fields or granular spacetime that preserve clarity while still producing redshift. The equations might look different, but they fit the same data. Perhaps the most radical mathematical overhaul comes from theories that redefine time itself. In conventional physics, time is a flowing variable, ticking forward in equations, but static models often treat it as a fixed coordinate, like latitude or longitude. This transforms the universe's timeline into a frozen landscape, where events don't unfold but simply exist. The math here borrows from quantum gravity and string theory, weaving time into the fabric of space as a static dimension. It's like replacing a movie with a sculpture. Every moment is there, just waiting to be observed from the right angle. Of course, no theory is complete without explaining inertia, why objects seem to resist changes in motion. Newton saw this as an intrinsic property of matter, but in a static universe, inertia might emerge from deeper geometry. Some equations suggest that what we feel as movement is really the universe's hidden structure guiding us along unseen paths, like a marble rolling through an invisible maze. This isn't just philosophical speculation. It's a mathematical framework that predicts real-world behavior without relying on motion. The beauty of these models lies in their audacity. They don't just tweak existing physics, they reimagine it entirely, proving that the cosmos can be described in more than one language. Whether they're right or wrong, their equations challenge us to think bigger, to question whether the universe's apparent dynamism is the only story math can tell. After all, if numbers can describe an expanding cosmos, why not a motionless one? The answer might not lie in choosing between them, but in discovering a deeper math that embraces both. The cosmic microwave background, that faint, almost imperceptible glow filling the universe, has long been considered the ultimate proof of the Big Bang. Detected in the 1960s as a uniform hum of microwave radiation, it was quickly interpreted as the cooled remnants of the universe's fiery birth. But what if this so-called afterglow isn't a relic of an explosive beginning at all? What if it's something far more mundane, a byproduct of processes happening right here, right now, in a cosmos that never expanded? One compelling alternative suggests the CMB could be the cumulative glow of countless stars and galaxies, their light scattered and reprocessed over eternity. Picture standing in a dense fog at night, surrounded by distant street lamps. Even if you can't see the individual lights, their combined glow would create a diffuse, uniform brightness all around you. In a static, infinite universe, starlight might behave similarly, traveling forever, bouncing off interstellar dust, and eventually blending into the microwave haze we detect today. This starlight soup theory isn't new. Physicist Sir James Jeans pondered it a century ago, but it was overshadowed by the Big Bang's rise. Yet modern simulations show that if the universe had no beginning, starlight could indeed pile up over infinite time, reaching equilibrium as a perfect thermal spectrum matching the CMB's uncanny uniformity. Then there's the idea of thermalization through particle interactions. In a universe filled with sparse but ubiquitous hydrogen, light could gradually lose energy through countless tiny collisions, like a ball slowing as it rolls through sand. Over eons, even visible starlight would degrade into microwaves, creating a background glow indistinguishable from a primordial fireball. Critics argue this process would distort the CMB's delicate temperature variations, but proponents point to quantum effects or undiscovered particle behaviors that might preserve those patterns without invoking expansion. Perhaps the most radical proposal comes from plasma cosmology, which suggests the CMB could be the signature of vast, galaxy-spanning electric currents. In this view, the universe is threaded with filaments of magnetized plasma, and when electrons spiral along these cosmic power lines, they emit radiation, including microwaves. It's akin to the way neon signs glow, but on a scale so immense it fills the entire sky. If true, the CMB wouldn't be an echo of creation, but the hum of an eternal cosmic engine, humming quietly in the background of a universe that simply is. The implications are profound. If the CMB has a local origin, then one of the Big Bang's strongest pillars crumbles. No explosive beginning, no rapid inflation, just an endless, steady cosmos where light and matter interact in ways we're still deciphering. This isn't about discarding evidence but reinterpreting it. After all, science thrives when we ask not just what does this mean, but what else could it mean? The cosmic microwave background might still be whispering secrets to us, but the real question is whether we're listening to the right story. For decades, dark matter has been the universe's most elusive ghost, an invisible substance thought to outweigh visible matter 5-to-1, yet slipping through every detector we've built to catch it. Scientists have scoured underground labs, scanned the skies, and even smashed particles at near light speeds, all hunting for the faintest trace of this mysterious material. But what if the hunt itself is based on a flawed assumption? What if dark matter doesn't exist because the phenomena it explains aren't caused by missing mass at all, but by our misunderstanding of motion itself? The case for dark matter hinges on discrepancies: galaxies spinning too fast, clusters bending light more than their visible mass should allow, cosmic structures forming in ways gravity alone can't explain. Each anomaly points to unseen matter tugging on the fabric of the cosmos. Yet after 40 years of searching, not a single dark matter particle has shown up where theory predicts. Some experiments have reported tantalizing hints, only for follow-ups to come up empty. Others, like the ultra-sensitive LUX Zeppelin detector buried a mile underground, have found nothing at all. This absence is so glaring that a growing number of physicists are asking, could we be solving the wrong puzzle? Enter the motionless universe. If galaxies aren't actually spinning the way we think, if their apparent rotation is an illusion created by how light behaves in a static cosmos, then the need for dark matter vanishes. Picture a carousel at night lit by flickering lamps. If the lights dimmed unpredictably, you might misjudge how fast it's turning. Similarly, if redshift and other measurements don't reliably track motion, our calculations of galactic mass could be wildly off. Modified Newtonian dynamics, or MUND, offers a mathematical framework for this, tweaking gravity's behavior at cosmic scales to match observations without invoking invisible matter. It's like realizing the carousel wasn't spinning too fast. Your stopwatch was broken. Critics argue MUND can't explain everything, like the bullet cluster, where two colliding galaxy clusters seem to have left their dark matter behind like cosmic shadows. But even here, static universe proponents have counter-arguments. If gravity operates differently in a motionless cosmos, or if electromagnetic forces play a larger role, the cluster's behavior might not require dark matter's gravitational glue. It's a reminder that anomalies often reveal more about our models than about reality. The trade-off is stark. Either we accept an unseen substance defying every attempt at detection, or we rewrite the rules of motion and gravity. Both options stretch credibility, but only one forces us to confront how much we might be misreading the universe's signals. After all, science's greatest breakthroughs often come not from finding answers, but from realizing we've been asking the wrong questions all along. Gravity, as we know it, is a dance of motion, planets orbiting stars, galaxies swirling through space, even apples falling from trees. Newton described it as a force pulling objects together, while Einstein reimagined it as the warping of spacetime by massive bodies. But in a motionless universe where nothing truly moves, these explanations crumble. If the cosmos is frozen, how does gravity still hold galaxies together or bend starlight? The answer might lie in rewriting the rules of physics itself. One bold idea comes from physicist Erik Verland, who proposed that gravity isn't a fundamental force at all. It's an emergent phenomenon, like temperature arising from the motion of atoms. In his framework, gravity emerges from the way information is arranged in the universe. a sort of cosmic hologram where what we perceive as attraction is really just the universe's hidden structure revealing itself. Picture a chessboard where the pieces seem to move on their own until you realize an invisible hand is sliding them. In a static cosmos, gravity could work similarly, not from moving masses, but from the way space itself encodes relationships between objects. Then there's modified Newtonian dynamics, or MUND, which tweaks the familiar inverse square law of gravity to explain galactic rotations without dark matter. In a motionless universe, MUND takes on new significance. If galaxies aren't actually spinning, their flat rotation curves might stem from gravity behaving differently at cosmic scales, not weakening as sharply with distance as Newton predicted. It's like discovering that the rules of magnetism change when you're not holding a compass near a fridge magnet, but surveying the entire Earth's field. Critics argue MUND struggles with galaxy clusters, but in a static framework, even those anomalies might dissolve if gravity's behavior is reinterpreted through a lens of stillness. Perhaps the most radical revision comes from theories treating gravity as a geometric illusion. If space-time isn't dynamic but frozen, then what we call gravitational attraction could be a trick of perspective, like mistaking the curve of a sealed glass globe for the pull of a planet. In this view, masses don't warp space-time. They're fixed points in an unchanging geometry, and the paths we perceive as orbits or falls are just the shortest routes through that eternal landscape. It's a vision that would make Einstein pause: relativity without motion, gravity without change. The implications ripple outward. If gravity works differently in a static cosmos, then black holes, those gravitational monsters born from collapsing stars, might not exist as we know them. Instead, they could be eternal structures, frozen singularities woven into the fabric of a motionless universe. Even gravitational waves, the ripples in spacetime detected by LIGO, might need reinterpreting. Could they be static vibrations like plucked strings on a cosmic harp that never actually moves? This isn't about discarding Newton or Einstein. It's about expanding their legacy. Just as they overturned the physics of their day, a motionless universe demands we rethink the very nature of attraction. Whether gravity emerges from information, bends new rules, or hides in frozen geometry, one thing is clear: the force that shapes the cosmos might be far stranger than we ever imagined. And that's where the real adventure begins. Black holes as we know them are cosmic whirlpools spinning voraciously, devouring anything that strays too close, their immense gravity warping space and time into an inescapable trap. But in a universe where nothing moves, where even the fabric of space-time stands frozen, these gravitational monsters would need an entirely new definition. Without motion, how could matter fall into a black hole? How could an event horizon, the point of no return, even exist if nothing crosses it? The answers might lie in reimagining black holes not as dynamic engines of destruction, but as eternal, unchanging structures woven into the very architecture of the cosmos. Picture a black hole not as a pit, but as a sculpture, a perfect, immutable dent in the fabric of spacetime. In this view, the event horizon isn't a boundary things move toward. It's a fixed feature, like the edge of a shadow cast by an object that never moves. Matter wouldn't spiral inward because there's no inward to spiral toward instead. It would simply exist in a state of eternal suspension, locked in place by the black hole's unchanging geometry. This isn't just philosophical musing. Some theories suggest that in a static universe, black holes could be topological defects, knots in spacetime that formed during some primordial phase transition, like cracks in ice as it freezes. These defects wouldn't evolve or interact dynamically. They'd simply be there, as permanent as mountains on a landscape. But what about the radiation Hawking predicted black holes should emit? In a traditional black hole, quantum effects near the event horizon produce a slow leak of energy, causing the hole to evaporate over eons. Yet in a motionless cosmos, time itself is illusory, so how could anything evaporate? One possibility is that Hawking radiation isn't a process at all, but a static feature, a halo of quantum fluctuations forever hovering at the horizon, never dissipating, never changing. It's like the glow of a neon sign that's always on, never flickering, because the concept of flicker requires time to pass. The most radical reinterpretation comes from holographic principles, which suggest that black holes might encode information on their surfaces rather than trapping it inside. In a static universe, this could mean that what we perceive as a black hole is just a two-dimensional pattern projected into three-dimensional space, a cosmic barcode stamped onto the sky. There's no interior, no singularity, just data frozen in an unchanging configuration. Imagine a tattoo on the skin of the universe, its meaning permanent, its form never fading. Of course, this raises new questions. Without motion, how do we explain the jets of energy screaming from quasars, or the way black holes seem to merge in violent collisions? The answer might lie in redefining what we're seeing. Those jets could be static structures, eternal beams of light caught in a cosmic tableau, their apparent dynamism just a trick of perspective. And merging black holes, perhaps they're not colliding at all, but simply overlapping patterns in spacetime's frozen tapestry, like two shadows crossing on a wall. The beauty of this reimagining isn't just in its novelty, it's in the way it forces us to confront our assumptions. We've always thought of black holes as the universe's most violent, active phenomena. But in a motionless cosmos, they might be its most serene, silent, unchanging, and eternal, not the end of things, but simply another way the universe can be. Entropy is often called time's arrow, the universe's relentless march from order to chaos, from hot to cold, from structure to dust. It's the reason ice melts in your drink, why buildings crumble over centuries, why stars eventually burn out. In a dynamic, expanding cosmos, entropy always increases, driving everything toward a quiet, uniform heat death. But what happens when the universe isn't moving at all? If time stands still and change is an illusion, does entropy still have meaning? At first glance, the idea of entropy in a static universe seems paradoxical. Without motion, there's no transfer of heat, no diffusion of particles, no irreversible decay. The very concept of disorder relies on things shifting, breaking down, rearranging. Yet even in a frozen cosmos, entropy might not vanish. It could simply freeze with everything else. Picture a snowflake suspended in glass. Its intricate structure isn't decaying, but it's still a snapshot of potential disorder, a moment of complexity preserved indefinitely. In this view, entropy isn't a process, it's a fixed property, etched into the fabric of reality like a carving in stone. Some theorists take this further, suggesting that what we call entropy in a static universe might just be the universe's default state, a single, eternal configuration where every possible arrangement of matter and energy already exists simultaneously. Imagine a library containing every book that could ever be written, with no librarian to shuffle them into disarray. The disorder isn't increasing because it was never ordered to begin with. This aligns with the block universe idea, where past, present, and future are equally real and unchanging. From that perspective, entropy isn't a force but a feature, like the grain in a piece of wood. But here's the twist: even in stasis, the universe might still obey the second law of thermodynamics, just differently. If entropy is a measure of possible states, a motionless cosmos could have maximum entropy by default, with no further increase possible. It's like a die that's already landed on every face at once. There's nowhere left to roll. This wouldn't violate thermodynamics, it would fulfill it perfectly, a universe that's reached equilibrium and stays there forever. Critics argue this undermines thermodynamics' predictive power. How do you explain why we perceive time's flow or the one-way nature of heat if entropy isn't actually changing? One provocative answer lies in consciousness itself. Our experience of time and decay might not reflect cosmic reality, but the way our brains navigate a static landscape. Think of a film strip. Each frame is unchanging, but the projector creates the illusion of motion. Similarly, our perception of entropy's rise could be the mind's way of making sense of a frozen universe's infinite complexity. The implications ripple beyond theory. If entropy is constant, the heat death of the universe, a fate where all energy is evenly distributed and no work can be done, might not be an ending but a starting point. A cosmos that's always been in equilibrium has no need to decay further. Stars wouldn't burn out because they're not really burning. They're fixed patterns in an eternal tapestry. This doesn't just challenge thermodynamics, it redefines what we mean by beginning and end. Ultimately, entropy in a motionless universe isn't about decay or disorder. It's about reimagining the very nature of existence. Whether it's a frozen snapshot, a timeless library, or a cosmic equilibrium, one thing is clear: the arrow of time might not be an arrow at all. It could just be a line drawn on a page, waiting for us to trace it with our eyes. Light traveling across the cosmos is one of our most trusted yardsticks for measuring the universe's scale and age. We watch photons that have journeyed for billions of years, assuming their speed never wavers, a constant 300,000 kilometers per second through the void. But in a motionless universe where expansion isn't stretching space, this simple picture gets turned on its head. If nothing's moving, how does light cover such vast distances? The answer might lie in rethinking some of physics' most sacred assumptions. One radical possibility is that the speed of light isn't fixed after all. What if photons slow down over cosmic distances, like a marathon runner gradually losing steam? This idea, known as variable speed of light theory, suggests that light's velocity could depend on the energy of the universe itself, slower in the past, faster now, or even fluctuating based on unseen factors. Imagine a beam of light not as a sprinter maintaining a steady pace, but as a traveler adjusting speed to match the terrain. In a static cosmos, this could mean redshift isn't caused by galaxies racing away, but by light itself arriving more sluggishly after an eons-long trek. Critics argue this would violate relativity's core tenets, but proponents point to quantum gravity models where light speed emerges from deeper, shifting physics. Then there's the mind-bending concept of timeless light. If the universe is truly motionless, then time, as we experience it, might not exist for a photon. From light's perspective, according to relativity, its entire journey happens instantaneously, no matter how far it travels. In a frozen cosmos, this takes on new meaning. Light doesn't travel at all. Instead, it's simply everywhere along its path at once, like a frozen bolt of lightning spanning the sky. What we perceive as a beam crossing space could be an eternal, unchanging thread woven through the universe's fabric. This isn't just poetic imagery, it's a mathematical reality in block universe theories where past, present, and future coexist. Another explanation lies in tired light, the idea that photons lose energy not because space expands, but through interactions with the sparse particles floating in the cosmic void. Picture a stone skipping across a pond, losing momentum with each ripple it creates. If light similarly, rubs against quantum fields or undiscovered particles over vast distances, its wavelength could stretch, producing redshift without any motion required. Skeptics note that tired light should blur distant galaxies, yet some refined models suggest mechanisms, like photons scattering without deflection, that preserve clarity while still draining energy. Perhaps the most startling reinterpretation comes from holographic principles, where light's journey isn't through space but across a hidden, lower-dimensional surface. In this view, the universe is like a movie screen, and photons are pixels illuminating a pre-rendered scene. There's no actual movement, just patterns revealing themselves in fixed relationships. This would mean the light from distant quasars isn't old, it's part of an eternal code, unfolding as we observe it. Each of these theories forces us to confront a profound question: is light a traveler or a marker? If the universe isn't expanding, then the stories we tell about cosmic distances and ancient photons might need rewinding. The light we see could be less a messenger from the past and more a feature of a universe that's always been there, waiting for us to look up and wonder. A universe without motion doesn't just challenge physics, it unravels the very way we think about reality. For centuries, human philosophy has been built on the idea of change. From Heraclitus's famous declaration that you can't step into the same river twice to modern theories of evolution and progress, we've framed existence as a story of transformation. But in a static cosmos where time and movement are illusions, every assumption about meaning, purpose, and even consciousness gets turned inside out. Take the concept of free will. If the universe is frozen, if every event, thought, and action exists eternally in an unchanging tapestry, then choice becomes an elaborate mirage. Our sense of decision-making might be like a character in a novel believing they're steering the plot, unaware they're just ink on a page. This isn't just theoretical, it echoes ancient debates about predestination versus agency. But unlike religious or deterministic frameworks, a motionless universe doesn't just suggest fate, it erases the distinction between past, present, and future entirely. There's no becoming, only being. Then there's the question of identity. We define ourselves through narrative stories of growth, struggle, and transformation. But if time doesn't flow, then who we are isn't a journey but a fixed point, like a statue with infinite facets. Imagine your life not as a movie unfolding frame by frame, but as a sculpture where childhood, old age, and every moment in between exist simultaneously. This reframes everything from memory to regret. There's no before or after to mourn or anticipate. Even death loses its sting, not as an endpoint but as another unchanging facet of an eternal whole. The implications for morality are just as profound. Ethics often rely on consequences, actions judged by their outcomes in a world where cause and effect unfold over time. But in a static universe, there are no consequences, only configurations. An act of cruelty and one of kindness might not be linked by causality, but exist as separate, frozen notes in a cosmic symphony. This doesn't negate morality but forces us to ask, without time, do good and evil become purely aesthetic like colors on a canvas? Even spirituality transforms. Many traditions envision enlightenment or salvation as a progression, a soul's journey toward harmony or transcendence. But in a motionless cosmos, transcendence can't be a destination because there's nowhere to go. Instead, awakening might mean perceiving the universe as it truly is, not a process but a pattern, not a becoming but a boundless, unchanging isness. Science fiction has toyed with these ideas for decades, from Jorge Luis Borges's Garden of Forking Paths to Christopher Nolan's Interstellar. But philosophy's deepest discomfort lies in reconciling a static universe with our lived experience of change. How do we square the sensation of time's passage with a reality where it doesn't exist? One haunting answer is that consciousness itself might be the only movement and illusion generated by minds tricked into perceiving slices of eternity as flux. This isn't just abstract speculation. It reshapes how we value existence. If the universe isn't evolving toward anything, then meaning isn't found in progress but in presence. Beauty, love, and discovery aren't fleeting, they're eternal, etched into the fabric of reality like stars in a frozen sky. The irony is exquisite. A motionless cosmos might not diminish life's significance but amplify it, revealing every moment as infinite. The real revolution isn't in the physics but in the perspective. A static universe doesn't just change what we know, it changes how we know, and that might be the most profound discovery of all. The idea of a motionless universe might sound revolutionary, even poetic, but to most cosmologists, it's a non-starter. The scientific mainstream isn't just skeptical, they're armed with decades of observations that seem to leave no room for debate. Take redshift, for example. When astronomers point their telescopes at distant galaxies, they don't just see a slight shift toward the red end of the spectrum. They see a pattern so precise it forms a straight-line relationship between distance and redshift, known as Hubble's law. This isn't a fluke or a misinterpretation. It's a consistent, measurable phenomenon across tens of thousands of galaxies. To dismiss this as anything other than cosmic expansion, critics argue, would be like insisting the Earth is flat after seeing the curvature from space. Then there's the cosmic microwave background radiation, the afterglow of the Big Bang. Its near-perfect uniformity and precise temperature fluctuations match predictions of an expanding universe down to the tiniest details. Alternative explanations like tired light or plasma interactions struggle to replicate these patterns without introducing ad hoc assumptions. As astrophysicist Ethan Siegel puts it, you can't just wave away the CMB. It's not a coincidence that its properties align perfectly with an expanding, cooling universe. It's a smoking gun. The skeptic's strongest weapon, though, might be time dilation. In an expanding universe, distant cosmic events like supernova should appear to unfold more slowly than nearby ones, their light stretched not just in wavelength but in duration. And that's exactly what we observe. Distant supernova flicker and fade at a predictably slower pace, as if space itself is stretching their light like taffy. A static universe would need an entirely separate mechanism to explain this slowing, one that so far lacks any plausible foundation in known physics. But the objections go deeper than individual observations. The motionless universe model struggles to explain why all these disparate lines of evidence, redshift, the CMB, time dilation, even the large-scale distribution of galaxies conspire to tell the same story. As cosmologist Katie Mack notes, it's not just one puzzle piece that fits the expanding universe model, it's the entire puzzle with every piece locking together. To reject expansion, you wouldn't just need an alternative for each observation. You'd need a reason why all these unrelated phenomena somehow mimic an expanding cosmos in perfect unison. Perhaps the most damning critique is mathematical. The equations of general relativity, which describe gravity and spacetime with breathtaking accuracy, naturally predict an expanding or contracting universe. To eliminate motion entirely requires bolting on artificial fixes, extra terms, hidden dimensions, or unexplained fields that feel, in the words of Nobel laureate David Gross, like trying to balance a pencil on its tip forever. The expanding universe isn't just one interpretation of the data. It's the simplest, most elegant framework that explains everything from the birth of galaxies to the fate of light. Yet even the staunchest critics acknowledge a kernel of truth in the motionless universe idea. Science advances by questioning orthodoxy. Every paradigm shift from geocentrism to quantum mechanics began with someone daring to say, "What if we're wrong?" The objections aren't meant to silence dissent, but to stress how high the bar is for overturning cosmology's most robust theory. After all, extraordinary claims require extraordinary evidence, and so far, the motionless universe remains a fascinating thought experiment in search of a breakthrough. But as history shows, sometimes today's heresy becomes tomorrow's textbook. The real question isn't whether the mainstream is wrong, it's whether we're asking the right questions to find out. Testing the motionless universe hypothesis isn't just about reinterpreting old data, it's about designing bold new ways to scrutinize the cosmos. Imagine launching a deep space probe unlike any before, one engineered to detect subtle anomalies in the fabric of space itself. Traditional missions like Voyager or New Horizons were built to explore planets and moons, but a probe designed for this purpose might carry ultra-precise atomic clocks, synchronized with counterparts on Earth. Over decades of travel, even the tiniest discrepancies in their timekeeping could reveal whether space is truly stretching or standing still. If the clocks drift apart in a way that contradicts expansion, it might hint at a universe frozen in place, where redshift and other phenomena stem from something far stranger than motion. Next, consider the potential of next-generation telescopes. The James Webb Space Telescope revolutionized infrared astronomy, but future observatories could go further, like the proposed LISA mission, a space-based gravitational wave detector. In an expanding universe, ripples in spacetime from colliding black holes should weaken predictably over distance. But if those waves arrive with unexpected signatures, perhaps patterns that suggest space isn't stretching as assumed, it could force a re-evaluation of cosmic dynamics. Even ground-based telescopes might play a role. By mapping the distribution of galaxies in unprecedented detail, astronomers could search for large-scale structures that defy expansion's predictions. If the universe's vast web of matter appears too uniform or too clumpy for an expanding model, the motionless hypothesis gains traction. Then there's the cosmic microwave background. While it's often cited as proof of the Big Bang, finer measurements of its polarization, the direction of its light waves might reveal inconsistencies. A static universe would leave different fingerprints in this radiation, perhaps subtle asymmetries or unexpected correlations between temperature and polarization. Experiments like the Simons Observatory or future CMB-S4 could provide the resolution needed to spot these deviations, turning the universe's oldest light into a litmus test for motion. But perhaps the most provocative test involves quantum physics. If light speed or behavior changes imperceptibly over cosmic distances, as some static models suggest, we might detect this by studying distant quasars. These ultra-bright galactic cores emit light with precise spectral lines. If those lines shift in ways that tired light or variable speed theories predict without the need for expansion, it could upend decades of assumptions. Even tabletop experiments on Earth, like those probing quantum gravity or the nature of vacuum energy, might uncover phenomena that favor a motionless cosmos. The beauty of these tests lies in their daring. They don't just challenge a theory, they challenge how we explore the universe itself. Whether through spacecraft, telescopes, or quantum labs, the quest to prove or disprove the motionless hypothesis reminds us that science thrives when we dare to imagine the unimaginable. After all, the universe doesn't owe us an easy answer, just the thrill of the search. Long before telescopes or quantum physics, ancient civilizations gazed at the night sky and saw not an expanding cosmos but a perfect, unchanging vault. The Egyptians envisioned the heavens as a goddess arched over the earth, her star-studded body fixed eternally in place. To them, celestial bodies weren't hurling through space, they were divine lanterns carried by gods along predetermined paths, as regular and unmoving as the Nile's annual floods. This wasn't primitive ignorance, it was an intuitive grasp of cosmic stability that eerily mirrors modern motionless theories. The Greeks took this further with crystalline spheres, a series of nested, transparent orbs holding planets and stars in perfect, unmovable harmony. Aristotle argued the heavens were made of an unchanging fifth element, ether, where motion was circular and eternal but never progressive. Unlike Earth's messy, decaying realm, the stars above were timeless, their positions so fixed they became the backdrop for measuring earthly change. Even Ptolemy's geocentric model, often mocked for its complexity, reflected a deep belief in cosmic constancy. Those elaborate epicycles weren't just mathematical hacks, they were attempts to preserve the illusion of a motionless sky while accounting for wandering planets. Half a world away, Chinese astronomers charted the heavens with similar reverence for stillness. The Kai-Tian cosmological model depicted the sky as an unshifting hemisphere over a flat Earth, with celestial bodies gliding like beads on invisible rails. Emperors built observatories not to track expansion, but to detect deviations from the heavens' perfect order, omens of earthly disruption. To these scholars, the universe wasn't a dynamic engine, it was a frozen clock, its gears eternally meshed. What's striking isn't just how often these cultures rejected cosmic motion, but why. Without modern instruments, they relied on naked eye observations, and to the unaided gaze, the night sky does appear static. Stars don't visibly recede, galaxies don't whirl like pinwheels. The heavens' apparent stability became proof of divinity, philosophy, even political order. When Copernicus and Galileo shattered this illusion, they didn't just move Earth from the center, they shattered an entire world, built on celestial permanence. Yet today's motionless universe theories echo these ancient intuitions in unexpected ways. Like Ptolemy's epicycles, modern alternatives to expansion, tired light, variable speed of light, or emergent gravity, aim to explain apparent motion without invoking a dynamic cosmos. The difference, where ancients lacked tools to probe deeper, we now confront a universe where both expansion and stasis leave traces in the data. The real lesson of history isn't that early cosmologies were wrong, but that they recognized a truth we're now rediscovering. Sometimes the universe's deepest secrets hide in plain sight, masked by the illusion of movement. Imagine waking up to headlines declaring the universe isn't expanding, that everything we thought was moving is actually frozen in place. The shockwaves would ripple far beyond scientific circles, cracking the foundations of how we see ourselves in the cosmos. For millennia, humanity's religions have woven motion into their creation stories, from Hindu cosmology's cyclical universes breathing in and out to the biblical image of God stretching out the heavens like a scroll. A motionless cosmos would force a profound reckoning. If there's no Big Bang, does that erase the moment of creation? Would faiths adapt by reframing divinity as an eternal sculptor, carving existence from unchanging marble rather than igniting a dynamic explosion? Some might embrace the stillness as proof of a perfect, finished creation, while others could see it as a divine pause, a universe holding its breath. Art would face its own revolution. Since the Renaissance, painters have captured celestial motion, Van Gogh's swirling stars, Dali's melting clocks bending time. Even modern installations like TeamLab's digital galaxies thrive on the poetry of movement. In a static universe, artists might turn to fractal geometry or infinite tessellations, finding beauty in frozen perfection rather than flux. Music, too, would shift without time's arrow. compositions could abandon linear progression for eternal harmonies, like Tibetan singing bowls humming a single, unending note. The very concept of a story might unravel, with narratives rejecting traditional arcs for vignettes suspended in an eternal now. Science fiction, that mirror of our cosmic anxieties, would rewrite its tropes overnight. Space operas rely on warp drives and galaxy-spanning empires, but how do you explore a universe where distance never changes? Writers might imagine civilizations trapped like insects in amber, their histories etched into static starlight. Films like Interstellar's time-bending Odyssey would give way to meditations on eternal recurrence, Groundhog Day on a cosmic scale. Even dystopias would transform. Instead of fearing heat death, we might dread eternal stasis, a universe where nothing decays but nothing grows. The psychological impact could be deepest of all. Human ambition thrives on change, the belief that progress moves forward, that tomorrow can be better. A motionless cosmos might trigger existential vertigo, as if we're characters in a painted mural, our struggles and triumphs mere brushstrokes in a finished work. Yet there's also solace in stillness. If the universe isn't racing toward cold oblivion, but resting in perfect equilibrium, it could inspire a new serenity, an invitation to live not as fleeting sparks, but as threads in an eternal tapestry. Perhaps the most fascinating question isn't how we'd adapt, but what parts of us would resist. After centuries of worshipping progress, could we truly embrace a frozen cosmos? Or would we, like ancient astronomers tracing epicycles, invent new stories to keep the illusion of motion alive? The answer lies not in the stars, but in our stubborn, beautiful refusal to accept that the dance might never have begun. Whether the motionless universe theory ultimately proves correct or collapses under scrutiny, its very existence serves as a vital pressure test for cosmology. Science advances not just by accumulating facts, but by confronting ideas that dare to dismantle its most cherished frameworks. Consider how quantum mechanics shattered classical physics in the early 20th century. What seemed like a tidy, deterministic universe gave way to a realm of probabilities and paradoxes. The motionless hypothesis could trigger a similar upheaval, forcing cosmologists to re-examine the invisible scaffolding holding up modern astrophysics. Take dark energy, that enigmatic force accelerating cosmic expansion. If the universe isn't expanding at all, then dark energy might not just be mysterious, it could be entirely unnecessary. Overnight, billions of dollars in experiments hunting for its nature would pivot from breakthrough pursuits to historical footnotes. Laboratories buried deep underground, designed to catch whispers of dark matter particles, might repurpose their detectors to probe alternative gravity models or quantum vacuum effects. The ripple effect would extend to funding agencies, academic departments, and even textbook publishers scrambling to rewrite chapters on cosmic evolution. But the real transformation would be philosophical. Cosmology's quest for origins, the search for a definitive starting point, would face an existential challenge. Without a big bang, questions like what happened before or what caused the beginning become meaningless in a timeless, unchanging cosmos. Researchers might shift focus from creation myths to mapping the eternal architecture of space, treating the universe less like a story and more like a frozen symphony waiting to be decoded. The very language of cosmology would change, swapping verbs like expand and evolve for terms like structure and configuration. Yet the motionless universe's greatest gift could be humility. Every paradigm shift in science, from geocentrism to relativity, has reminded us how easily we mistake perception for truth. If this theory gains traction, it wouldn't just rewrite textbooks, it would reaffirm science's core ethos, that no idea, no matter how fundamental, is immune to scrutiny. The cosmos owes us no obligation to conform to our intuitions. Its deepest truths often lurk where we least expect, not in the grand sweep of motion, but in the quiet spaces between assumptions we never thought to question. Einstein's abandoned cosmological constant wasn't just a historical footnote, it's become a ghost haunting modern physics. When he reluctantly discarded his static universe model in the face of Hubble's expansion evidence, he left behind a tantalizing question: what if the math was right but the interpretation wrong? Today, a small but growing cadre of physicists are dusting off Einstein's equations and injecting them with bold new possibilities. Take physicist Joe Megiddo's work on variable speed of light theories. By allowing light's velocity to change over cosmic time, his models recreate redshift effects without requiring space to stretch, effectively rebooting Einstein's static cosmos with a quantum age twist. The numbers show something startling: a universe where the cosmological constant doesn't balance expansion, but replaces it entirely through evolving physical constants. Then there's the holographic principle's radical reimagining. If the universe is fundamentally a two-dimensional information structure projected into three dimensions, like a cosmic mirage, then apparent motion could be an emergent illusion. Theoretical physicist Eric Verland's emergent gravity framework takes this further, suggesting what we perceive as cosmic expansion might actually be the universe's quantum information rearranging itself on unimaginably small scales. Picture a frozen lake cracking under its own weight. The ice isn't moving outward, but new structures form within its stillness. These models don't just tweak Einstein's static vision. They transform it into something far stranger, where space-time itself is secondary to hidden quantum relationships. Observational astronomers are joining the fray with fresh data challenges. The James Webb Space Telescope's discovery of unexpectedly mature galaxies in the early universe has thrown a wrench into standard cosmic timelines. In an expanding cosmos, these ancient behemoths shouldn't have had time to form. But in a static model, their existence might simply reflect an eternal universe where structure formation never had a starting gun. Even dark energy surveys are yielding oddities. The DAISY instrument's recent 3D map of the universe's large-scale structure shows subtle inconsistencies with expansion predictions patterns that, some argue, align better with a universe where clustering occurs through timeless gravitational interactions rather than dynamic growth. The most provocative revival comes from quantum gravity researchers like Lee Smolin, who propose that Einstein's static solution might describe not our observable universe, but a deeper, timeless reality underlying it. In this view, the expanding cosmos we perceive could be a fleeting fluctuation within an eternal static background, like a temporary whirlpool in an otherwise motionless ocean. It's a cosmic twist worthy of Borges. The universe appears dynamic not because it is, but because we're trapped in the one region where time's illusion holds sway. What makes these modern takes compelling isn't their wholesale rejection of mainstream cosmology, but their willingness to ask which assumptions deserve re-examination. Einstein's original static model failed because it couldn't explain Hubble's redshifts, but today's theorists have quantum mechanics, holography, and precision cosmology at their disposal. They're not merely resurrecting an old idea, they're stress-testing whether our entire cosmic narrative rests on mistaking shadow for substance. Whether they succeed or fail, their work guarantees one certainty: the question of cosmic motion is far from settled. The multiverse concept shatters the idea of a single, unified cosmos, replacing it with an endless sea of universes, each bubbling into existence with its own laws of physics. But what happens when you drop a motionless universe into this frothing cosmic soup? At first glance, the two ideas seem incompatible, one frozen in eternal stillness, the others bursting with infinite variation. Yet some of the most cutting-edge theories in physics suggest these opposites might not just coexist, but depend on each other in ways that rewrite our understanding of reality. Picture a vast, unmoving ocean, its surface perfectly smooth, its depths untouched by waves. Now imagine countless ripples dancing across that surface, each one a separate, dynamic universe. This is the vision of physicists like Leonard Susskind, who propose that what we perceive as our expanding universe could be a temporary fluctuation within a far larger, static multiverse. In this model, the Big Bang wasn't the beginning of everything, just a local event in an eternal, unchanging background. The motion we observe, merely the way our limited three-dimensional slice interacts with higher dimensional geometry. It's like mistaking the flicker of a candle's flame for the entire history of fire. String theory takes this further, suggesting that the motionless bulk of higher dimensional space could anchor countless dynamic universes like ours. Imagine a loaf of raisin bread where the dough never moves, but the raisins inside expand away from each other as the bread bakes. In this analogy, the dough represents the static multiverse, while each raisin is an individual universe experiencing its own apparent expansion. What's startling is how neatly this solves one of the motionless universe's biggest puzzles. If nothing's moving, why does everything look like it is? The answer might lie in our perspective. We're trapped inside the raisin, oblivious to the unmoved dough beyond. Quantum mechanics adds another layer. The many worlds interpretation, where every quantum decision spawns new universes, typically depicts an ever-branching tree of reality. But what if that tree is frozen? Physicists like Julian Barber argue that every possible outcome, every branch already exists in a timeless multiverse, with our sense of motion just an illusion as we move through pre-existing states. It's like flipping through a deck of cards. The sequence feels dynamic, but the cards themselves never change. In this hybrid model, a motionless multiverse contains infinite dynamic-seeming universes, each a static frame in the cosmic film strip. The implications are dizzying. If our expanding universe is just one facet of a deeper, unchanging reality, then dark energy and cosmic acceleration might not be fundamental forces. They could be side effects of how our local bubble interfaces with the static whole. Even the arrow of time, that relentless march from past to future, might emerge from our limited view of a multiverse where every moment eternally exists. This isn't just blending two theories, it's weaving them into a tapestry where motion and stillness aren't opposites, but different threads of the same fabric. Critics argue this smacks of metaphysical speculation, but supporters point to concrete math. Brain cosmology, for instance, derives precise equations showing how a static higher dimensional space could host expanding universes. The real test may come from gravitational wave astronomy. Future detectors might catch whispers of collisions between our universe and others, or anomalies that reveal the hidden architecture of the multiverse. Until then, the hybrid model remains a tantalizing possibility, that the universe's greatest illusion isn't just motion, it's thinking we're alone in the void. If our reality is a vast simulation, an intricate digital construct running on some unfathomable cosmic computer, then the illusion of motion takes on a whole new meaning. Think of a video game where every frame is pre-rendered, every character's path predetermined. The world feels dynamic, alive with movement, but beneath the surface, it's just code executing in sequence. Could the universe operate the same way? Some digital physics theorists argue that what we perceive as cosmic motion, the whirl of galaxies, the dance of particles, might simply be the output of a program so advanced its stillness is masked by the sheer fluidity of its calculations. This idea finds roots in the work of visionaries like Edward Fredkin, who proposed that the universe operates on discrete computational principles. In his finite nature hypothesis, reality isn't continuous but built from tiny, indivisible units of information like pixels on a screen. Motion, then, isn't the smooth glide we experience but a rapid flicker between frames, each one static until the next update. A motionless universe fits eerily well here. If time itself is just a series of frozen snapshots, then the cosmos isn't expanding or contracting. It's being reloaded moment by whatever or whoever runs the simulation. Even stranger is the concept of clockless computing, a real-world technique where chips process data without a central timer, tasks complete when ready, not on a rigid schedule. Scale this up to a simulated cosmos, and you get a universe where change isn't driven by time's flow, but by the completion of discrete operations. Redshift could be a rendering artifact, dark energy a buffer overflow, and the cosmic microwave background the simulation's idle hum. The illusion of motion, just the system's way of keeping our local reality consistent, like a video game loading only the parts of the world you're looking at. But here's the twist: if we're in a simulation, a motionless universe might not be a bug, it could be a feature. Rendering trillions of moving galaxies in real time would strain even an alien supercomputer. Far more efficient to pre-compute every state in advance like a cosmic flipbook, and let observers experience the illusion of continuity. This aligns with physicist Cela's Bean's suggestion that simulators might impose a lattice on spacetime to conserve resources, subtly breaking physics at tiny scales. If true, our search for cosmic motion could be like NPCs in a game trying to detect their own loading screens. The philosophical implications are staggering. If the universe is static by design, then free will becomes a carefully crafted mirage, entropy a narrative device, and the Big Bang just the simulation's boot-up sequence. Even our attempts to study cosmology might be part of the program, a scripted quest for truths that don't exist outside the code. Yet this isn't necessarily dystopian. A simulated stasis could explain why physical constants are so finely tuned for life. The parameters weren't random but set. The universe isn't winding down, it's just running exactly as written. Of course, not all simulations need be static. Some models suggest a dynamic, self-updating reality where consciousness itself drives computation. But the motionless version offers a haunting elegance. A universe that feels alive because we're wired to perceive it that way, while its true nature remains as still as a paused video. Whether this is genius or madness depends on one question: can we prove the pause button exists? Until then, the simulation hypothesis reminds us that reality's deepest truths might not be hidden in motion, but in the spaces between the frames. What if the universe's motion isn't out there in the cosmos at all but inside us? This startling possibility bridges ancient philosophy with cutting-edge quantum theory, suggesting that the dynamic universe we perceive might be a cosmic-scale optical illusion created by the very act of observation. Consider the double-slit experiment where particles behave differently when being watched. At the quantum level, consciousness seems to play an inexplicable role in shaping reality. Now scale that up to the entire universe. Could the grand celestial dance of galaxies and the arrow of time itself be consequences of how conscious beings interact with the cosmos? Eastern mystics have pondered this for millennia. Hindu cosmology describes the universe as the dream of Brahman, where divine consciousness breathes life into static form. Buddhist teachings compare reality to a spinning firebrand when whirled rapidly. It creates the illusion of a continuous circle, though no true motion exists. These aren't just poetic metaphors. Modern neurobiology reveals that human perception constructs motion from discrete neural snapshots, like how a flipbook still images create fluid animation. What if cosmic motion works the same way? The universe might be projecting its own celestial flipbook, with consciousness as the projector's light. Quantum physics adds weight to this speculation. The von Neumann-Wigner interpretation suggests consciousness causes the collapse of quantum wave functions, meaning reality doesn't fully exist until observed. Apply this to cosmology, and the implications become staggering. The redshift of distant galaxies might not indicate actual movement, but rather how our observation crystallizes probabilities into what we perceive as cosmic history. It's like walking through a forest at night with a flashlight. The beam doesn't create trees, but determines which ones become visible. Similarly, our observation could be lighting up specific configurations of a fundamentally static universe. Even cosmic time might be an artifact of perception. Neuroscientist Carl Friston's free energy principle proposes that brains evolve to predict causal sequences, creating the sensation of time's flow. In a block universe where past, present, and future coexist, consciousness could be the needle stitching these moments into linear narrative. Imagine a record album sitting motionless on a table. Only when the needle touches vinyl does music seem to unfold in time. Our awareness might play that same role for the cosmos, transforming eternal stillness into the symphony of cosmic evolution we call the Big Bang, star formation, and galactic rotation. The most radical version comes from participatory anthropic principle, which posits that observers literally bring the universe into being. In this view, the universe appears 13.8 billion years old, not because it is, but because that's the minimum timeline needed to produce conscious observers who can ask the question. It's not that stars move, it's that our perception demands a story with motion to make sense of the patterns. Like a detective reconstructing a crime scene, we assemble cosmic clues into a narrative of expansion, unaware we're projecting the very dynamics we claim to discover. Critics argue this veers into solipsism, but proponents point to concrete mysteries. Why does the universe appear fine-tuned for life? Why do quantum experiments change when observed? The motionless consciousness model offers a unifying answer because reality isn't separate from the act of perception. Just as a video game renders only what the player sees to save processing power, the cosmos might manifest motion and change only where consciousness looks. The rest could remain in quantum potential, an infinite, unchanging background. This isn't about dismissing science but expanding its boundaries. If consciousness and cosmos are entangled, then studying one illuminates the other. Future experiments might test this by searching for anomalies in regions devoid of observers, like the far side of the moon, or probing whether cosmological measurements change when made by AI versus human minds. The answers could reveal whether motion is the universe's property or our mind's way of making it comprehensible. After all, the night sky's stillness has always held a secret. The most profound revolutions begin not with movement, but with how we choose to see. If the universe is truly motionless and eternal, unchanging tapestry where every event, from the birth of stars to the rise of civilizations, exists simultaneously, then our deepest assumptions about purpose and progress start to unravel. Human history has been built on the belief that time moves forward, that our actions ripple into the future, that tomorrow can be better than today. But in a static cosmos where before and after are illusions, what does it mean to strive, to innovate, or even to care? Consider the ethical weight of choices. When we fight for justice, preserve ecosystems, or push scientific boundaries, we do so with the conviction that our efforts will shape a future that doesn't yet exist. But if every moment is equally real and unchanging, then the suffering we aim to alleviate and the breakthroughs we celebrate aren't outcomes we influence, they're fixed points in an infinite tableau. A child born into poverty, a forest saved from destruction, a cure for disease, these aren't victories or tragedies unfolding over time, but permanent features of the cosmic landscape. At first glance, this seems to drain meaning from our struggles, yet there's another way to see it. If every act of kindness and cruelty is eternally part of the universe's structure, then their significance isn't diminished, it's set in stone. This reframes the very notion of responsibility. In a dynamic universe, we might justify inaction by arguing that consequences are temporary or that future generations will solve today's problems. But in a motionless cosmos, there are no future generations, only an eternal now where every life, every species, and every ecosystem exists in unalterable relation to everything else. The ethical imperative shifts from change the future to honor the pattern. Preservation isn't just pragmatic, it's a recognition that the world's beauty and fragility aren't passing phenomena, but indelible facets of reality itself. Even ambition takes on new dimensions. If progress isn't a march toward improvement, but an exploration of pre-existing possibilities, then discovery becomes less about conquering the unknown and more about bearing witness to the universe's infinite complexity. Think of it like uncovering a masterpiece painting hidden beneath layers of grime. The artwork was always there, but the act of revealing it still holds profound value. Scientific breakthroughs, artistic creations, and societal transformations might not advance a static cosmos, but they illuminate its richness, allowing consciousness to map the contours of an eternal design. The real challenge lies in reconciling this with our emotional lives. Humans are wired to celebrate growth and mourn loss, to feel the urgency of time slipping away. A motionless universe doesn't negate these feelings, it contextualizes them. Joy and grief aren't reactions to change, but experiences etched into the fabric of existence, as permanent as the stars. In this light, the question isn't whether progress matters, but how we redefine it. Perhaps meaning isn't found in altering the universe's trajectory, but in fully inhabiting our role within its unchanging grandeur, like actors embracing their lines in a play where the script is timeless, but the performance still aches with truth. Ultimately, the ethics of a motionless cosmos don't erase human agency, they relocate it. Our choices may not shape what's already whole, but they determine how we align ourselves with that wholeness. To live well in such a universe isn't to lament the absence of motion, but to recognize that every act of courage, creativity, and compassion is a stroke in a masterpiece that was, is, and always will be, unfolding not in time but in the infinite depth of now. The motionless universe theory doesn't just tweak our understanding of the cosmos, it throws open the doors to a radically different way of seeing everything. For centuries, science has operated under the assumption that change is the universe's default state, from the spin of electrons to the rush of galaxies. But what if we've been mistaking the map for the territory? What if the universe isn't a dynamic engine but a frozen masterpiece, and we're simply the ones moving through it? This idea isn't just a fringe curiosity, it's a profound challenge to the stories we tell about time, space, and our place within them. Think of it like standing in a hall of mirrors. From one angle, you see endless reflections, each seemingly in motion as you shift your gaze. But the mirrors themselves aren't moving, it's your perspective that creates the illusion. The motionless universe theory suggests the cosmos operates similarly. What we've interpreted as galactic flight, cosmic expansion, even the flow of time itself, might just be tricks of the light. This isn't about dismissing the mountains of evidence supporting an expanding universe, but about asking whether we've been reading that evidence through the wrong lens. After all, history is littered with scientific revolutions that began when someone dared to question the obvious, from Earth's place in the solar system to the quantum weirdness lurking in every atom. The real power of this idea lies in its ability to unsettle. It forces us to confront how much of our cosmic narrative rests on assumptions we rarely examine. Take the Big Bang. We've all seen the animations, a tiny point exploding outward, birthing galaxies like sparks from a firework. But strip away the assumption of motion, and that narrative crumbles. Suddenly, the afterglow of creation might just be the hum of an eternal machine, the redshift of distant galaxies, a cosmic sleight of hand. Even dark energy, that mysterious force accelerating expansion, could vanish from the equations entirely, replaced by subtler, stranger physics we're only beginning to grasp. Of course, skepticism is healthy. The scientific method thrives on doubt, on testing bold ideas against cold, hard data. The motionless universe faces formidable hurdles, from explaining the precise patterns in the cosmic microwave background to accounting for the observed time dilation in distant supernova. Yet every revolutionary theory starts as an underdog. Einstein's relativity was once dismissed as mathematical fantasy. Quantum mechanics seem to defy all common sense. The point isn't whether this theory is right, it's that science moves forward when we're willing to ask, what if we're wrong? So where does that leave us? However you feel about the motionless universe, one thing is certain. It's a reminder that reality is far stranger than our intuitions suggest. Whether the cosmos is expanding, static, or something beyond our current imagination, the act of questioning is what keeps science alive. So toss your thoughts into the comments. Could the universe truly be standing still, or is motion woven into its very fabric? The answer might not just change how we see the stars, but how we see